Well, in the last couple of sections, we've been talking about how we can find linear equations from graphs, from patterns, from tables, from context, from story problems. And we've been applying a lot of the tools that we've learned about linear equations in order to do that. Well, today we're going to kind of practice that again, but in a slightly different way. The I can statement for 511 is I can understand and compare. So we are going to be comparing linear equations that come to us in different formats. So different pieces of information or different ways they're presented. We're going to try and use the tools that we've got in order to figure out what's going on and then compare those and then answer questions about them. So if you take a look at the warm-up question, it says write the linear equation that represents the data in the table in slope-intercept form. So this is one of those where we're missing our starting point. Remember, we always need a point and we need a slope, or we need the rate of change. This one doesn't have that starting point. It doesn't have 0 on it. 0 would be right in between the two of these. Now the fact that it's right in between -1 and +1, that's really useful because we can use our rate of change to kind of figure out what this is. So we might look at this in a couple different ways. The thing I want you to notice is what's happening here. Can we look at this pattern and can we figure out what the rate of change is? So you'll notice that from -1 to +1 it went from -6 to +2. From 1 to 3 it went from 2 to 8. 2 to 10, and then from 3 to 5 it went from 10 to 18, and from 5 to 7 it went from 18 to 26. So one thing that might be helpful is let's figure out what the rate of change is and see if we can match things up here. So I'm going to go ahead and I'm going to find the rate of change between these 2 points. So y2 minus y1 would be 10 minus 2, and x2 minus x1 would be 3 minus 1. So that's going to be 8 here and 2 on the bottom, so that's going to be a 4. So the fact that our rate of change is positive, what that means is it's going up. These are getting bigger, so as the x's get bigger, the y's get bigger. And you'll notice that this skips, so from 10 to 18, this is going up 8. From 18 to 26, this is going up 8. And the reason for that is we're going from 3 to 5. We're skipping 2 units on every single one of these. So there are a couple things that we could do to figure out what this starting point is. Since we're going from 1 back to 0, we're just going to back up 1 rate of change. We're just going to back up 4. So that's going to put us at -2. If we backed up again, -1, we'd back up another 4, so that would be -6, so that works out just fine there. Let's fill in one of these other ones. 3 and 5, right in the middle there, would be a 4. So over here, if we were to count up from here, that would be a 14. And if we were to count down from here, down that rate of change, that would be a 14 also. So it does kind of fit the pattern right here. So when they're skipping between some of these numbers on the x, we've got to skip between some of these numbers on the y. So here's our rate of change. Our rate of change would be 4. This is our initial value right there. So we're going to write down y equals 4x, and then the starting value would be -2. And again, if we wanted to double check any of this, let's just plug in a number. Let's plug in a 7 and let's see if we get out a 26. So if I put a 7 right here, 4 times 7 minus 2, that would be 28 minus 2. That is 26, so it checks out. So we do have the correct equation right there, so we can rely on that. Okay, so for today, here's what we've got as far as the type of problems that we're going to see. So it says use equation A and table B below to complete the problem. So it says find the rate of change for each. So on this one, this is equation A, and this is table B. And you'll notice that this table runs horizontally, so we're going to need to be a little bit careful with that. I think this is the first time we've seen those, but you will see occasionally data presented that way. On this one, the rate of change is pretty easy. Remember, when they say rate, you're going to automatically think slope. So the slope on this one is 5/2. Okay, so we've got that one taken care of. That's for A. And I'm going to do B in blue here. So if we wanted to find the rate of change here, there are a couple different things we could do. We can try and figure it out in our head or something like that. But I'm going to do this. This is going to be y2 minus y1, and this is going to be x2 minus x1. Now, when these are stacked like this with the x's on the top and the y's on the bottom, we've got to be careful to flip that around. So we're going to do 1 minus minus 3. And we're going to do 1 minus 0. This would work with using any of these pairs of points. Just make sure you put the y on the top and the x's on the bottom. So this is going to be, let's see, this is a plus, so that's going to be 4 over 1. So that means the rate of change on this one is a 4. So we found the rate of change on both. Even though they were given in different formats, we did find the rate of change for both. It says find the y-intercept for each one of them. Now again, on this one here, it's really easy because they told us exactly what it is. The y-intercept on A is a -3, and again I'm writing that in red. And the y-intercept on this one, notice that when the x is 0, the y is -3. So on that one it's also -3. Whoops. So they have the same starting point on both of these, same y-intercept on both. It says which one has the greatest rate of change, the biggest rate of change. So this is a fraction, an improper fraction, so we need to think of this as 2.5. So the rate of change here is 2.5, the rate of change there is 4. So we're going to say B because the rate is 4. That's the biggest one, that's the greatest rate of change. If x is equal to 10, which one has the greatest y value? Okay. Now, take a look over here. They've given us the equation so we can find any y value we want. So if we were to say 5/2 times 10 minus 3, let's see what we get here. Those are going to cancel off. That's going to be a 5. 5 times 5 is 25 minus 3, so we end up with 22. Okay, so this one has a y value of 22. So I'm just going to write that right here in red. Okay, that one has a y value of 22. Now the trouble with this one is 10's not in our table and we don't have an equation yet. So let's come up with an equation for this one. They didn't ask us to, but we kind of need this. So our rate of change is 4. Our starting value, that's why it's nice to have those figured out, is -3. So if we were to plug in a 10, this would be 4 times 10, whoops, minus 3, so that would be 40 minus 3, so that's going to be 37. So 37. So if x is equal to 10, these are our two answers to choose from. It says which one has the greatest y value. That would be B, okay, because it's equal to 37. So I'm going to circle that guy right there. And then it says, what does x need to be to make y equal to 17 for each one? Now, we haven't done a whole lot of this, but this is the way this works. Most of the time, they give us an x value and we plug it into the equation like we did to answer D. But on this one, they're saying, what does x need to be so that y is equal to 17? So on this one, we're going to do this. We're going to put a 17 right there. So we're going to say 17 equals 5/2 x minus 3. And then we'll go ahead and solve that. So I'm going to add 3 to both sides. Those are going to cancel. I get 5/2 x equals 20. And then I need to multiply by the reciprocal. Remember, there's a fraction in front of the variable, so we're going to multiply by the reciprocal. So I'll do that. Those are going to cancel. And I noticed over here, look, I flipped that over, so I need the reciprocal. The reciprocal would be 2/5. I'm going to cancel. 5 goes in here once, 5 goes in here 4 times, so we multiply those together, we get an 8. So we get x equals 8 on that one. And for the other one, we're going to do the same thing. We're going to put a 17 right here. So this is going to be 17 equals 4x minus 3. Kind of nice that we don't have any fractions to deal with. So we're going to add 3. Okay. So we get 20 equals 4x. Divide both sides by 4. So we get x equals 5 on this one. Okay. Now it didn't ask us to, make any conclusions about these. It just says what does x need to be to make y equal to 17 for each one of them. So we put a 17 in here and we solved for what x needs to be. So for a, it's got to be 8. and for B it's got to be 5. Okay, each one of those would produce a 17, and if we double check that, watch what happens if we put a 5 in here. 4 times 5 is 20, 20 minus 3 is 17, so we're in good shape there. And on this one, if we plugged in, there's the equation right here, so if we plugged that in here, this would be 5 halves times 8. The 8 and the 2 would cancel to be a 4. 5 times 4 would be 20 minus 3. We end up with that 17 like we want. Okay, let's take a look at example 2. It says, find the rate of change for each function represented below, and then order the rates from least to greatest. So we put them in order. So let's see what we've got here. This is an equation, regular old linear equation. We can tell that just by looking, but it's not in the right format. So what I'm going to do is I'm going to put this in slope-intercept form. I'm going to, well, let's see, let's move this to the other side. So we get negative y equals negative 3x plus 2. And then again, we don't want this, so we're going to divide everything by a negative 1. So that's going to give us y equals, that would be 3x plus, oops, that's a negative, because we're going to divide each one by a negative 1, minus 2. So the rate of change on this one is 3, so I'm going to circle that. Now, think about this one. This is y equals a number. This would be y equals 0x plus 1. So the rate of change on this one is 0. Okay, in fact, I'm going to write m equals on each one of these just so we can keep track of that. Remember, the slope is the same as the rate there. And then let's look at this one. Let's see, what have we got going on here? We've got a graph. So let's see if we can find some convenient points where we can use them to find the slope, to find the rate. That is a good point right there. And I think that is one. Yeah, that looks pretty good. We kind of do that stair-step pattern and we get these. So this would be a rise of 1 and a run of 2. You do want to make sure that these are scaled the same way. Each one of these does count as 1, 1, 2, 3, 4, 5, and then the same up here. So this is a rise of 1 and a run of 2. So that means the slope on this one is 1/2. Okay, so we've got those so far, and then we've got to take a look at this one, and this looks like a bit of a mess. Now there is a little trick that we can use here. Rather than using either one of these with the fractions in them, let's use these two, no problem skipping between the two of these. So this would be 3 minus 2, y2 minus y1, over x2 minus x1, so that's going to be 6 minus 3. So this is going to be a 1 on the top and a 3 on the bottom. So the slope on this one is 1/3. And then it said order them from least to greatest. So if we ordered them from least to greatest, they'd go like this. B has the smallest one because that was 0. And then let's see, of 1/2 and 1/3. 1/3 is smaller, so that would be D, rate of change of 1/3. And then C with a rate of change of 1/2. And then function A, that one has the highest rate of change. That's going to be a 3. Okay, so we've got all the work to support it, and then we've got them in order. I suppose you could just put B, D, C, A, and we could call it good. But the nice thing is, then we've got our work right here. Everybody can look at this and say, oh, they know what the rate of change is for each one of them, and I can see why they ordered them that way. So let's take a look at problem 6 from your assignment. It says Jeremy and Mac both attend Elkridge Middle School, but Jeremy rides his bike while Mac rides the bus. The graph below models Jeremy's distance from the school as he rides his bike. The equation models Mac's distance from the school as he rides the bus. Then we've got a couple parts here. So part A, find the equation for Jeremy's trip. Okay, so here's Jeremy's trip. We've got to find an equation for that. Graph Mac's equation. So we'll probably just graph Mac's equation over here. Determine who travels farther to get to school, and determine who takes less time to get to school. So let's take a look at this. We'll break this down. And I'm going to do Jeremy's in red, and I'm going to do Mac's in blue so we can kind of keep those straight of who's who as we're looking at the equations and the work and the graphs and that sort of thing. So it says find an equation for Jeremy's trip. All right, so let's come over here on Jeremy's trip and let's figure out what's going on here. Okay, this is 4 kilometers where he starts, and then this is how many minutes it takes him to get there. So you'll notice that these axes are scaled differently. So if we find the slope, we better be really careful. We've got a convenient point right here and right here. So we're going to go down 1 and over 2 boxes. But again, we've got to be really careful on this. This is down from 4 to 3. So this is down 1 kilometer. So I'm going to write -1, whoops, -1 kilometer. The rise is -1 kilometer. And then the run, look at how many minutes that is. Okay, that's 2 minutes and that's 4 minutes. So he reduces his distance to school 1 kilometer in 4 minutes. Okay, now this is a story problem, so if you want to use fractions or decimals, either one would be okay. I'm going to kind of keep it in fraction form because I like that a little bit better, because it kind of lends itself to slope and, rise and run and stuff like that. So we're going to write -1/4. Okay, so there's the rate of change. That's the slope if you want to think of it that way. And then the y-intercept is 4. Okay, so this is what m is on our problem, and then the y-intercept would be 4. Okay, now if we take a look over here and look at how they've written the equation, they've changed variables on us, which is totally okay. What they did is d equals -1/2 t plus 8. And down below they said t is time in minutes and d is distance in kilometers. So this is where the x normally is. So this is like the x, and notice that that's time in minutes, so that's like the t. And then d for distance, that's exactly how we've got this set up. This is like the x, this is like the y, this is like the x, this is like the y. So let's write both of these equations using the same variables here. So we're going to write d equals, okay, so again, if we're thinking y equals mx plus b, we're going to be thinking d equals mt plus d, or plus b. Okay, so this is -1/4 t, whoops, almost did that, and then plus 4. Okay, so this is the answer to part A. All right, so we've got the equation for Jeremy's trip. Then it says graph Mac's equation. So we've got to take this equation, we've got to graph it over here. So I'm going to change to blue. Here's our y-intercept. We're going to start at 8. And then it needs to be -1/2. And remember, we can't just go down 1 and over 2 blocks. We've got to keep this in mind. This is -1 kilometer on the top, just like we had here, and this is 2 minutes on the bottom. So we're going to go down 1 kilometer, and then we're going to go over 1 minute. Or sorry, over 2 minutes. 1 kilometer down, 2 minutes over. This box represents 2 minutes. Box vertically represents 1 kilometer. So we're going to go down 1 kilometer over 2 minutes. Okay, down 1 more kilometer, so 6 kilometers now. 2 minutes, we're going to go from 2 to 4. So it looks like this. So you do have to be really careful when you're graphing things like this. But this should be a little bit comforting. Now take a look. We get that nice line. I'm going to make mine a little bit straighter. We get this nice line, and the fact that they both end at the same place should be a little comforting because they said they were going to school. Okay, so they should end up at the same place. Okay, so we've got the graph of Mac's trip over here in blue. We've got the equation for Jeremy's trip here in red, and it says determine who travels farther to get to school. Well, let's think about that. What are we looking for here if we're talking about who travels farther, who covers more distance? Well, that wouldn't be the minute axis, that would be the kilometer axis. That would be what their starting point is, their distance from school. So to me it looks like the blue one, so this is Mac, he starts at 8 kilometers away from school, whereas Jeremy only starts 4 kilometers away from school. And you can kind of see that right here. Here's Jeremy's initial value of 4, and here's Mac's initial value of 8. Determine who travels farther to get to school. So I'm going to change colors here, and we're going to say Mac travels farther. Okay. And I'm going to put the answer right there, 8 kilometers. Okay, he travels 8 kilometers. And then it says determine who takes less time to get to school. Who takes less time to get to school? Well, let's see. Well, how many minutes does it take Jeremy to get to school? If he starts off at 4 kilometers from school, he would be at school when he gets to 0 kilometers. So that takes him 6 minutes, or sorry, 16 minutes. Now, Mac lives further away, but he also gets there in 16 minutes. So the answer to this one is, determine who takes less time. We're going to say they both take 16 minutes. So it's a tie. All right. They leave at the same time, and it takes them 16 minutes to get there. So they both get there at the same time. But Mac had to travel much further. He had to travel twice as far. So I guess that begs the question, who's going faster? Who would be going faster? Well, if you stop and think about it, the person that's going faster covers more distance in the same amount of time. So Mac is going faster. So I'm going to write this down. Mac is faster. Now that kind of makes sense because he's on the bus, right? And if you take a look over here, if we took at our rates of change, this would be, he can cover a kilometer in 4 minutes. That's what we figured out. He can cover a kilometer in 2 minutes because he's on the bus. He's going twice as fast as Jeremy is on his bike. Okay, that's a great in-depth problem, a great exposure to the type of thing you're going to see on the assignment. And we've done the last one for you, so good luck with that.